So in general, whenever we apply divide and conquer, we usually end up at a recurrence equation like this. And there are three methods for solving this kind of recurrences: the substitution method, the recursion-tree method, and the master method. Before we move on to discuss each of those methods, there are some details to be ignored. The first thing is that it doesn't matter if this is an integer or not. We divide the original problem of size n into several sub-problems. And so to divide the size by some constant b, okay, and it doesn't matter if this is an integer size or not. Even if it's not an integer, it will not affect the conclusion anyway. The other one is we always assume that the time complexity for solving the problem with very small n is a constant. Okay, so it takes a constant time, very few steps to solve for very small size problems. For example, like n equals 2 or 3, or say any number less than 10. Alright, now let's check out those three methods one by one. We start from the simplest one, which is the substitution method. The whole point of substitution method is to make a good guess. Then try to prove that conclusion by induction. So it's very important to make a good guess. So for example, if we have a recurrence equation like this, what do you think? It looks quite familiar, right? I think it's pretty safe to guess that the complexity is n log n, right? Now let's try to prove it. So step one is to make a good guess and try to prove it by induction. To prove by induction means we assume that this is true for smaller integers, like assume it is true for any integer that is strictly smaller than n. And we try to prove that this is also true for n itself. Okay, and if this is true for all the integers smaller than n, in particular, certainly it is true for this m, half of n. Right? So for any m, t of m is bounded above by a constant times m times log m. Right? So we assume that there exists a constant c so that t of m for this m is bounded above by this constant times m times log m. Alright? So substitution means we substitute this inequality back into this recurrence equation and try to obtain the same conclusion for t of n. Alright, so substitute into the recurrence, we get this is the expression for t of n, and substitute the right hand side of this inequality into this equation, we get this is less than or equal to 2 times this constant times half of n times log of half of n plus n. Since we're trying to prove an upper bound, it's safe to remove all those floors. And then once these are removed and we obtain something like c times n, and these two are cancelled out, times log of half of n is equivalent to log of n minus log 2, right? And plus this n. So we have c n log n minus something. If we assume that this is log with base 2, then here we have 1, right? So it's minus cn plus n. If this constant is greater than or equal to 1, then minus cn plus n is going to be a negative number, or at least a non-positive number, right? So it's safe to say it's bounded above by this constant times n log n. So this inequality is not only true for all the m that is strictly less than n, but is also true for n itself, and that completes the induction. Yet be careful here. We have one question say, yeah, how about n equals 1? Well, if n equals 1, that means log n is 0. Therefore, we have something like t of 1 is less than or equal to 0. It doesn't sound right. But hey, relax. When we prove by induction, we don't have to be always starting from t of 1. As long as we can prove that for sufficiently large constant c, it is true for either t of 2 or t of 3 for small numbers. Okay, we can start from any sufficiently small numbers and say if this is true for a small number, and then we assume that this is true for all m which is strictly smaller than n, and if we can prove that it is true for this n, then still it works. A very important point here is that when we try to prove the conclusion, we must prove the exact form. We're going to see what I mean by saying exact form here. Let's take a look at another example. Still, we're looking at the same equation, but let's make a wrong guess. Let's try to prove that the complexity is big O of n, the linear function, not n log n. Can we prove it? We'll say the first step is still the same. Let's assume it is true for all the smaller integers. For all m that is strictly less than n, in particular for this m being half of n. Alright? And let's assume that this is true for any m, which means there exists a constant c so that t of m is less than or equal to c times m. And when this m is particularly half of n, this is true. Alright? Now let's substitute it into the original equation. What do we get? We have t of n is 2 times t of half of n plus n, and which is bounded above by 2 times this one, right? 2 times the constant times half of n plus n. And when we're talking about less than or equal to, it's safe to remove the 4, and we have this 2 and this 2 cancelled out, and therefore we have a constant times n plus n. Can we conclude that this is, well, c plus 1 times n, but c plus 1 is also a constant. It's another constant. So can we claim that this is simply big O of n? And the answer is no, that is not true. Because what we're trying to prove is that if this inequality is true for all m, which means t of m is bounded above by a constant times m for all m that is strictly less than n, we must prove that t of n is bounded above by this constant, this same constant, times n, without adding anything. That's what I mean by saying we must prove the exact form, exact same form. Okay, in other words, if this is t of m bounded above by c times m, it has to be t of n bounded above by c times n, right? And if there's an extra n, it doesn't work. So be careful here. Well, so with substitution method, the trickiest question is how to make a good guess. And that's why we have our next method, the recursion-tree method. That is the method to help us make a good guess. Okay, judging from its name, the key is to construct a recursion tree. We draw our conclusions based on constructing a recursion tree. Let's look at another example. So this is the equation we have. It's like we partition the original problem into 4 parts, but somehow when we combine them, we only need 3 of them. And with big theta of n squared time to combine the solutions. The recursion tree is like this. We start from the root, where the root is t of n, and we break it down like this. It means it takes a constant times n squared time to combine all the solutions. And before we do so, we have to do 3 recursions. Okay, so recursively break each one down into a constant times a quarter of n squared, because at this level the size of the problem is a quarter of n. So instead of having a c times n squared, we have c times a quarter of n squared. Okay, plus 3 recursions. And it's true for each one of them. And we keep going like this. So each t of n over 16 is going to be replaced by what? By a constant times n over 16 squared, right? So it's going to be like this. And we keep breaking until finally we get all those t of 1s as our leaf nodes in this recursion tree. Alright, so my first question is, what is the height of this tree? Now think about it. So how do we get from n to 1? So we start from 1n and then divide n by 4, n by 4, n by 4. So we keep dividing n by 4 until we get 1, right? So for how many times that we divide this n by 4 in order to get 1? So the height is log n, right, with base 4, because every time we divide it by 4. So the total time complexity, T of n, is the sum of everything. To calculate the total sum, we can sum up each level first. So for the first level, we get a constant times n squared. On the second level, we get something like a constant times a quarter of n squared, then times 3, right? So it's like 3 over 16, that's 4 squared, 16 times a constant times n squared. Alright, and how about this level? Can you find the pattern here? It's going to be 3 over 16 squared times another cn squared. Right? So the total sum will be the sum of all those terms, plus on the last level a constant for each t of 1. So how many t of 1s? How many leaf nodes do we have? It's like we start from 1, and then we have 3 branches, and then we have 3 squared branches, right? And then we have 3 cubed branches, and so on and so forth. So altogether we're going to have what? 3 to the power of something. 3 to the power of what? It depends on the height of the tree, and this is the height of the tree, right? So eventually we're going to have 3 to the power of the height of the tree. And it's equivalent to this form, n to the power of log 3 with base 4. Now you see how we obtain those strange exponential functions. N to the power of, this is something less than 1, right? And therefore, on the last level, we have something like big theta of this n to the power of log 3 with base 4. So to sum them up, we get T of n is the sum of all those terms plus the last level. So what is this? Well, first of all, Cn squared is a common factor that can be taken out, right? So the key is to calculate this sum. It's easier to obtain an upper bound. it's safe to say that since each term is a positive number, it's safe to say that this is bounded above by this infinite series, right? When we add up the first several steps, it's certainly less than the sum from 0 to infinity. Okay, so what is the value of this series? It's a convergent series, right? I hope you can still remember some conclusion from your calculus class. What is the Taylor expansion of 1 over 1 minus x? Do you still remember? That's the infinite sum of x to the power I. So in this case, that specific x is just 3 over 16. So that infinite series converges to 1 over 1 minus this x, and then multiplied by cn squared plus big theta of n to the power of something. And well, that something is smaller than 1. Okay, so basically this is a constant times n squared. And compare these two terms, we take the larger one as our final conclusion, and therefore it is big O of n squared. And we say that this is a relatively simple case because this recursion tree is balanced. Okay, let's look at another example where the tree is no longer balanced. A situation like this. All right, and therefore we start from t of n and break it down into a constant times n, and then with two parts, t of a third of n plus t of 2/3 of n. And while each part is then broken down into a constant times the current size plus two other recursions. And similar thing for this part. Okay, so we're going to recursively break each part into two parts and keep going. But obviously you can see that the tree is no longer balanced because starting from n along each path we're eventually getting to t of 1, but in a different speed. And so what is the height of this tree? Well, the longest path is the rightmost path. It's like every time we divide n by not 2/3, it's multiplied by 2/3. It's the same as to divide n by 3/2, right? It's the reverse, right? Every time we divide n by 3/2, and eventually we're gonna get 1 at some point, right? And for how many times that we should divide n by 3/2 to obtain 1? That gives the height of the tree. What is that? Another log n, right? With the base 3/2, right? And t of n is the total sum of everything in this tree. So again, let's calculate them level by level. On the first level, we get c times n. On the second level, we have c times 1/3 plus 2/3. It's another c times n. And how about the third level? Is 1 plus 2 plus 2 plus 4 over 9. It's another constant times n. It looks so nice. It's like on every level we're going to obtain constant times n, the same term. But remember that this is not a complete tree. So eventually at some level we're going to get something that is less than Cn. But it's too complicated to, draw the whole tree and carefully examine each level. And it's not really necessary. You just say, roughly speaking, each level is bounded above by a constant times n, right? And there are altogether log n levels. So put them all together, it's safe to guess that this is bounded above. It's big O of n log n. Well, this is not a strict proof, but instead it gives us a pretty good guess of the conclusion. And therefore, we can then prove by substitution. The proof by substitution is like we assume that this conclusion is true for any number m which is strictly less than n. Which means what? In particular, if m is 1/3 of n, it should be true. And if m is 2/3 of n, it's also true. And therefore, we can claim that there exists a constant d, so that this t of m is smaller than or equal to d times m log m. And this is also true for this part. For this m, this t is also bounded above by d times m times log m, plus the last term, c times n. Okay, put them all together and simplify it. We get something like d times n log n. That's what we're trying to obtain. It's dn log n minus dn times some number plus a constant times n. What we really need is to prove that this is less than or equal to dn log n. And we can obtain this conclusion only if this part is negative. Can we guarantee that? N doesn't matter, n is a positive number. Alright, so what we really need to prove is that negative d times this constant plus c is less than or equal to 0. Right? To solve that equation, we have that if d is greater than or equal to this constant, then we can prove that if we assume that t of m is smaller than or equal to this d times m log m, then this is also true for this n with the exact form. And that completes the proof. So the point of having this recursion tree method, sometimes it can help us to obtain a pretty good upper bound. Or sometimes if it's too complicated to obtain the exact answer, at least we can make a pretty good guess. And then we can prove that guess by substitution.